Topic Notes 2.3, Weathering, Erosion, and Sedimentation. This picture was taken down in Winley Key Fossil Coral Reef State Park down in the Keys, and there you get the opportunity to actually walk down into the quarries and get in the old limestone, which essentially is built up from a lot of coral skeletons from the past. Now remember, Florida has been submerged and of course exposed many times as sea levels have changed. And so this actually shows you that because those islands were essentially made out of coral reefs in the past, just like you can find similar types of marine fossils throughout Florida in the limestone. And it's really neat to go in the sea there. So we are going to be, in this note set, starting to deal with the backside of those big geologic processes that form things. Now we're going to look at the weathering and erosion that actually breaks it all down and exposes it. And sometimes it gives us the history of what came before, like what you can find in Winley Key. So let's get started. Big idea today. The balance and combination between weathering, erosion, and sedimentation determines the type of shorelines that form. And as always, make sure to pay attention to the individual learning goals as you go through the notes. If we're going to start talking about breaking down of rocks in geology, let's start with weathering. Weathering is the wearing down or breaking of rocks through physical, chemical, and organic means. And we're going to go through each one of those. This is an example of that. This is a picture I took at Pictured Rocks National Lakeshore, which is in the Upper Peninsula of Michigan along Lake Superior. It's a great place because the weathering has essentially exposed Cambrian rock, which is really, really old. So there's a lot of history we can actually learn through this process of examining weathering and eroded rock formations. Now, there are three different types of weathering we'll talk about. The first is chemical. Now, in chemical weathering, the chemical composition of rocks changes through exposure to water and oxygen. Now, when rocks are exposed to precipitation or moving water, ions are dissolved from the rocks, and that's really important. A very important one would be calcium, for example, that gets dissolved from the rocks, and then it can be removed, and we'll talk about that a little bit more in the process of erosion, which has more of a transport quality to it. But for weathering, we're just talking breaking it down, that kind of a thing. Now, we also have something called oxidation that occurs. Now, this occurs a lot of times when there's a chemical reaction with oxygen that forms essentially an oxide or a metal oxide. You've probably seen this before in rust because this happens like when you have metal lying around and it gets exposed and it starts to get that reddish stuff on it. We can see that in rocks that have iron in it as well. And the lava that comes out in the ocean is mostly basalt, and that has iron in it as well, and that can cause an oxidation reaction. So these are chemical changes that can occur. Next up, we have physical weathering. Now, this is where rocks are broken into smaller pieces without changing their chemical composition. Now, this can happen in a couple of ways. For example, if you have constant temperature change all the time, that can actually weaken the structure of the rock itself. Also, if you look at the bottom picture, it talks about water and ice. If water gets into the cracks of a rock and freezes, remember water expands and becomes less dense when it freezes, that can actually pop rocks essentially. It can start to create a wedge that starts to break them. Now, wave action along the shoreline is also a good form of this. Both physical and chemical weathering can work in combination on a shoreline due to that. And there's a picture of blowing rocks, which is up in Jupiter. And as the waves crash on the limestone there, it actually shoots up in geysers in those big wave action days, which is really kind of cool. And you can see that not only is that water dissolving the rock, but it's also working to break it apart and transport it away as well. So that's where physical and chemical sort of come together. Then we have organic or biological weathering, where we have living things that actually work to break things down. Now, this relies on, again, these living organisms and can be a form of both chemical or physical weathering. Kelp, for example, which if you don't know what kelp is, it's the long algae that look like plants. They're very, very tall. They can be 20, 30 feet tall or more in the Pacific Northwest of the US. They have holdfasts on the bottom, and then they reach up into the sunlight for photosynthesis. Now, they can release sulfuric acids that break down calcium carbonate rock from their root structures. And so that helps them kind of work their way into the rocks, and their roots, of course, help to break things apart as they grow, just like roots of trees on land do. Now, rock-boring organisms like clams will actually drill depressions into the rock, which is, again, physical weathering. Then lichens, which can grow on top of rocks, even in terrestrial habitats, can release compounds that break down the rocks into smaller particles as well. And of course, we mentioned the roots of trees. So essentially, living things have ways to break all of this stuff down as well. So we've talked about weathering. Now let's look at erosion. So erosion is the natural process where materials are worn away from the Earth's surface and transported elsewhere. So this is really the part that has the transport mechanism. And you can actually see this is a picture from Maui, and you can see the waves crashing and then all the water draining away. That's that transport component. Now, the rate of erosion often depends on the size of the average waves. In recent studies, we've been looking at that. So the stronger the wave action, the more erosion you're actually going to have and the more transport away you're going to have. Now, erosion can occur in a few different ways, and we'll first tackle ice erosion. Now, the great example of that is glaciers. Now, as glaciers move over land, they're huge, they're massive, they've got a lot of weight, and they crush and break rocks below, and then eventually, essentially transport them with the ice as the glacier moves. Now, the sediments that are formed are then carried along. Now, here in the pictures, you can actually see on the bottom right how that happens. There's a graphic representation. The little gravel and pieces of sand are grinding and moving along with the ice. Now on the left in the center, you'll see pictures from Lawton Glacier, which is a glacier I got the chance to go climb up on in Alaska, which was awesome. And you can tell there's all sorts of rocks and gravel and stuff mixed up into the ice that is being transported, as you see that picture right there. Now, there's a bit of a crevasse you can see in the middle there, and we were there in the summer, where a lot of the ice was melting into water. And as the water ran down that crevasse, you could actually hear the flow rushing underneath the ice, and that rush was taking and transporting those sediments. Now, of course, you got to be very careful because falling down those crevasses under the ice would be quite dangerous. But you can also see in the picture where I'm standing there in the rock and gravel and ice, you can see where the gray landscape goes up to a certain point on either side, and then it's the green plants growing. That is where the glacier used to be. And of course, it has decreased in size over the years with climate change, things like that. But essentially, when the glacier retreats, it leaves all of that stuff wherever it happens to be at. Now, glaciers have had a huge impact on the geology of the planet because as these glaciers have formed during various different ice ages, for example, they move things around, sculpt the land as they go. So they're really important in terms of geology. Now, gravity erosion works in conjunction with weathering. Falling, collapsing rock structures essentially is all we're talking about here. And a great example of that is Darwin Arch in the Galapagos. Now, this is an icon of the Galapagos. People have been taking pictures of it and filming it for a ton of time. And in 2021, actually just about a month before this recording, the arch collapsed, and a dive boat happened to be there, and they happened to take a picture of it, and it was a big thing on the news. But this just goes to show you that even our iconic landscape is constantly changing, and gravity is one of those things that takes its toll. Speaking of taking its toll, wind has that ability too. It can pick up small particles and pieces of sand and sediment and then carry them to new locations. Now, this can happen, of course, in desert areas where there's a lot of sand particulate around, but it can happen in other habitats and ecosystems as well. Now, water erosion is definitely something we talk about quite a lot. Now, this is where moving water picks up sediment and carries it to new locations. Now, water can work, again, both as a weathering factor and force and an erosional force. And we see that a lot of times in canyons, for example, because not only are they dissolving the rock, but they're also transporting it elsewhere. And we see this also in rivers. For example, there's the Amazon River Delta. And you can kind of know just from your own knowledge here, as the river flows out to sea, it's bringing sediments with it. Those sediments get detached, they get transported and deposited somewhere else, usually in the delta, which forms a bunch of sandbars, things like that. So let's take a moment and do some definitionals here. So sedimentation is the deposition of suspended particles from the water. And of course, deposition is a geologic process where sediments, soil, and rocks are added to a landform or a land mass. These are important concepts when we're talking about coastal communities and coastal marine habitats. Now, as we already mentioned, we have that continental shelf area, which is exposed to a lot of sediments and, of course, deposition of those sediments. And so that creates that sort of layer on the continental shelf. And then, of course, when we look off the shelf in the continental slope and rise, those sediments are going to change composition. And we're going to talk a little bit about that in a bit. It goes from being less land-based to being more organic-based sedimentation that goes in that way. And if you look globally in the oceans, this kind of just gives you a bit of a sweep of what type of sediments are generally found there. Now, the heterogeneous sediments are essentially land-based. It's sort of eroded and weathered rock particles, sand grains, things like that come out. And if you notice, they're really connected to the continents. Now, if you move away from the continents, you start to get into things like carbonate oozes, siliceous oozes, and clay. These are generally related to organic deposits. All right, the two factors that impact the rate of sedimentation is particle size and water speed. Now, on the table to the top right, it shows you the different particle sizes from silt all the way to gravel, the larger stuff, right? Now, on the graphic on the bottom, it kind of lays out the order of deposition. Essentially, the larger the particle size, boulders, cobbles, things like that, they're going to settle first in terms of the speed or the rate of flow of water. And silt and clay are going to settle out last. So let's break this down. The faster the water moves, the larger the size of particles it can carry. As the water slows, larger particles will fall out of suspension and deposit first. The smallest particles, the silts and clays, are going to stay suspended in the water for longer, and they're going to travel longer distances. The graphic on the right is essentially a standardized sort of model for this process that includes the diameter and grain size in millimeters on the x-axis, and the y-axis, the velocity of the water in centimeters per second. And then it shows you regions in terms of combination of grain size and velocity where you get deposition, areas where you get transport based on that grain size and velocity, and areas where you get erosion, meaning that not only is it going to transport it, but it's going to actually pick it up and take it away, erosional forces. So it's just a general guide, but you can still see here that clay and silt are going to be the smallest grain sizes that are going to be transported from the smallest velocity of water current. So why do we care about learning about all these particle sizes and flow rates and things like that? Well, this has to do with the coastal communities we are going to be studying this year. Now, first, we're going to start off with what is the littoral zone. The littoral zone is the area where the land meets the sea. It's the intertidal zone, and we're going to be learning about tides soon. Now, the shape of the shoreline depends on two factors. First of all, the geology of the land lying closest to the shore. So essentially, is it big, mountainous, rocky? Is it more low-lying? Things like that. And then the second thing is the level of exposure to processes of weathering, erosion, and sedimentation. Now, here's another definition for you. Morphology is the study of the form of things. So in the case of the shore, we're going to look at the slope of the shore and the size of the sediments, which are the focus of shoreline morphology. Now we're going to look at some examples. Now, we are also going to go into these habitats in a little bit more detail later on down the line, but we're just focusing on shoreline formation and morphology. Now, for rocky shores, the shoreline is characterized by, you guessed it, rocky substrates, and can be sometimes very nearly vertical cliffs to wide, flat expanses of rock. Kind of depends on the slope. And it tends to be made of granite or igneous rocks, but also we can also have them out of sedimentary rocks as well, especially here in Florida. Now, rocks occur along a gradient. Larger rocks are going to occur farthest from shore. Smallest rocks are going to be nearer the low water mark, more weathering and erosion in that area. There's also going to be very little sedimentation due to the speed of the water. You're going to have a lot of currents and wave action, and that's going to move a lot of the sediments. So the sediments aren't going to deposit so much here. Now, sandy shores are made up of loose deposits of sand, a lot of times silica, but also small pieces of gravel and even shells. And they're formed by the process of erosion of sandstone and sedimentation of particles by waves. So there's a lot of moving around and shifting of the sand as we go. And that constant motion is due to the wind and the waves. And there tends to be a more gradual slope towards the ocean. Muddy shores are found in more protected areas where you have very little exposure to weathering and erosion. And there's almost no slope, very, very little slope to the shoreline, and almost no water movement. This allows the deposition of fine silt particles and organic materials, and that creates that muddy scenario. And sedimentation is the primary factor in the formation of muddy shores. And if you've ever walked in mud, and you can see the footprints here, you'll know what that means. Now, we're going to talk about estuaries in more depth later, but essentially they're formed in sheltered or partially enclosed areas where fresh and salt water meet. They're brackish water. They're sheltered, so weathering and erosion action of waves tends to be lower. The bottom is made up of fine sand and silt. There can also be some muddy areas as well, and the water is often murky with high turbidity. Now, turbidity is the level of transparency loss the water has due to the presence of suspended particles. So essentially it's how clear the water is based on those suspended particles. The higher their turbidity, the harder it is to see through the water. Now, a delta is a low-lying triangular area at the mouth of a river formed by the deposition of sediments. I've actually used the term delta a few times already today. Now, the river picks up sediments as water moves along, and as the rivers widen and approach the sea, the water speed tends to slow, and that slowing of the rate of water flow tends to begin the settlement process. Over time, sediments deposit, creating sandbars and other small land masses, forming a large fan-shaped structure. Now, the last little thing we're going to talk about has to do with the different types of marine sediments that we have. Now, these are all based on how they're formed. Hydrogenous sediments, for example, are sediments that are formed from seawater through chemical processes, such as carbonate, phosphorates, and magnesium nodules. Interestingly enough, magnesium nodules are something that actually industries are looking for to mine underwater. Now, we tend to talk a lot more about biogenous sediments, which are sediments from living organisms, crushed coral, mollusk shells, plankton shells, things like that. Now, in the deep sea, it's almost completely composed of this type of sediment, especially the remains of plankton. Now, lithogenous sediments, also pterogenous sediments, you'll see them interchanged, are produced from the erosional processes acting on continental rocks. And that's wind, water, freezing, thawing, all that stuff we've been talking about. And those particles are carried from the land by water, wind and ice, and gravity, and they end up along especially our coastal regions. They are primarily deposited on continental shelves, so you'll see them a lot on our beaches. They can be mixed up with biogenous sediments as well, but they're definitely more continental derived. All right, that is it. So the big main idea, again, the balance and combination between weathering, erosion, and sedimentation determines the type of shorelines that form, and of course, all of those learning goals underneath. So until next time, keep learning.